Hello everyone, I'm Rafał and I'm speaking to you from Poland, from Krakow, and I will tell you about caching and especially about caching in the context of microservices deployed on Kubernetes. But first, a few words about myself. I'm a cloud software engineer at Hazelcast. Before I worked at Google and CERN. I'm also an author of the book Continuous Delivery with Docker and Jenkins. From time to time, I do training and speaking, but my main job is I'm a software engineer. And as I said, I live in Krakow in Poland. Also, a few words about Hazelcast. So Hazelcast is a distributed company. We produce open source software and we have 3 products. First one is the most known Hazelcast in-memory data grid. This is what people usually use for caching. Our second product is Hazelcast Jet, which is a library for stream processing. And the last product is quite new, is Hazelcast put into as a service in the cloud. Our agenda for today is pretty straightforward. So there will be a very short introduction about caching and the microservices. And then we will walk through all possible caching patterns that you can use in your microservices deployed on Kubernetes. While I'll be talking, I would like you to think about 2 things. First thing is, in your software, which of this pattern do you use? Because this list is complete, so you must use one of this pattern. And the second thing I would like you to think about is, would it make sense to change to any other pattern? Would it make sense for my system, for my architecture? Okay, let's start. So this is a short introduction. So in general, that's a diagram for Microservice World. So we have a lot of microservices. They have different versions. They can be written in a different programming languages, and they use each other. And now the main question when it comes to caching is, where is the right place to put your caching layer? Is it inside of each microservice, or maybe as a separate unit in our separate deployment? Or maybe we can put cache in front of the microservices. And that's what this talk will be about. So starting from the first caching pattern is the simplest thing you can imagine. It's embedded cache. So embedded cache is when you put your cache as a library inside your application. So the flow is as follows. Request goes to our Kubernetes service, which forwards the request to one of the Kubernetes pod, and application receives the request. Then the application checks in the cache, which is embedded. Have I already executed such a request? If yes, return it from cache. If no, do some business logic, put it into cache and return the response. So the idea is very simple. The cache goes together with the application. It's that simple that we could think even about implementing this on our own. If you use Java, that is probably how your code could look like. So we create a concurrent hash map, then we process the request, check if the request is in the cache. If yes, get the value from the cache. If no, do some processing, put it into cache and return the response. So you can implement it yourself. However, please don't do it. Don't do it because a simple collection in Java or any programming language is not a cache. It's not a cache because it has no eviction policy, no max size limit, no statistic, no built-in cache loaders, no expiration time, no notification mechanism. So it lacks a lot of features that you will need later. So you're way better off by using some caching library. So what is a good caching library for Java? A very simple, if you just need anything as a library, is like Guava Cache is a very, very, very good caching solution where you can define all these parameters up front while building the cache. Another good solution is EH Cache. We can even take this idea of caching one layer higher and put the cache into application layer. So if you happen to use Spring, that is how your caching could look like. So you just add a cacheable keyword. Now every call to the method getBookName by ISBN will first check in a book's cache if there is such value. If yes, return it from the cache. Only if there is no cached value, we will execute the method findBook in slow source. But be careful, because Spring for some reason uses concurrent hash map by default. So you are better off, first thing you do in a Spring application, change your cache manager, for example, to Guava or any other caching library. So this is our diagram for embedded cache. So this is pretty simple, but there's one big problem about this caching. Imagine that the first request goes to Kubernetes service and it's forwarded to the pod on the top. We do some business logic, we put value into the cache and so on. Now, there is a second request, which is the same. It goes to Kubernetes service, but this time it's forwarded to the application at the bottom. So the application needs to do this business logic once again, because these caches are completely separate. They don't know about each other. That is why one of the improvements to the embedded cache is embedded distributed cache. So it's still the same idea. If you think about the patterns, it's still the same pattern. However, this time we will use a different caching library. So this time we will use for caching, we will use Hazelcast, which is the distributed cache. And this time it looks exactly the same, flow is exactly the same, but all caches, all embedded caches in all applications, they form one consistent caching cluster. So this is how it would look like in your Spring application. If we stick to the Spring example, if you would like to use for all your cacheable, would like to use Hazelcast as a cache, all you need to change is to add Hazelcast as a cache manager, and then for the caching layer, Hazelcast is used. Now, you may think like, okay, I start my applications like I start two instances of my applications. They both have like cache. And now, how do they form the cluster? How do I configure this? Because you see on this slide, there is no configuration, but they will still form the cluster. And we thought how to make it very convenient to the users. And we came up with the idea of the discovery plugins. So now for every like deployment environment, we have a discovery plugin, which uses API of the given environment to discover other members and to form a cluster. It's not only to discover members, it's also to provide like high availability, to distribute across, distribute the partitions across the zones and so on. So you can choose for the, from the plugins. There is like now very trending like Kubernetes plugin, which is the most relevant to this presentation. So if you are interested in details, how to use it, we publish blog posts, but in general, there are two modes you can use. One is that plugin uses Kubernetes API and queries the Kubernetes master to detect other members. And the second mode is to use DNS resolution. So we read records from the DNS to find other members. And it's all done dynamically, automatically. So that is the good part. So that is our diagram for embedded distributed cache. It works really good. Actually, Kubernetes is like very good for that. So short pros and cons of embedded cache. So from the good sides, configuration is very simple because the cache goes together with application, so you don't really need to do anything. The latency of the data is very low because the cache goes together with your application again. And there is no ops team or ops effort needed because it goes together with your application. However, from the downsides, the cache management is not flexible. If you would like to scale up your cache, I would like now not to have 2 nodes, but I would like to have 5 nodes of cache. You can do it only together with your application because it's embedded. It's also limited to your language of choice. If you write in Java, then it will be limited to the JVM-based solutions. And the last downside is that data is collocated with your application, which may be a bad thing or not such a big deal. That will depend on probably your enterprise. From our experience, like big enterprises, they don't want to have their data together with the application, even if it's just a cache. No, they just want it separate. Okay, we covered embedded cache. Now, the next one is client-server topology. So client-server is a little bit like a database. So we set up a caching server and application connects to the caching server. Flow is like this. Request goes to Kubernetes service, it goes to the Kubernetes pod, to the application, and then application uses cache client to connect to the cache server, which is deployed completely separate from the application. And if you think for a moment, like, what is the difference between this diagram and this diagram, like from embedded cache? There are 2 main differences. First one is obvious. We have this guy on the diagram, and this guy needs separate like management, but it also gives us flexibility. We can scale it up, down as we want. We can do whatever we want with the cache server. That will also mean you will usually need some ops team to manage this, or just part of the developer's time. Like it can be a DevOps team. It can be like that doesn't necessarily need to be a separate team, but definitely some time to manage this, to maintain this server. Now, there's a second thing on this diagram that is very different from the embedded cache, and this is this part. So now we use cache client to connect to cache server. And the thing is that cache client can be written in totally different language than cache server, because there is a well-defined protocol and you can use it like in a different language. And that is a very common strategy, that you set up the cache cluster or a lot of cache clusters, and then there are a lot of applications written in different programming languages and they use this cache. That is a very common approach in the microservice world. It's so common that most caching solutions, like the most popular Redis or a little old school but still popular Memcache, they are designed to work from client server mode, and it's actually the only way they can work. Like Redis is, I guess, written in C, so you cannot really embed it in a natural way into your application. Now, how to deploy like cache server and cache client? If we stick to the Hazelcast example and we would like to deploy it on Kubernetes, so obviously for Kubernetes, we provide a Helm chart or an operator where you can just start the cache server and scale it up, down, upgrade, whatever you want. Now for the client part, if we stick to the Java example and Spring Boot, and Spring, this is how it would look like, the cache manager. So we define like client config, and then we say, use this Kubernetes plugin. This is what I described before, to discover the cache server. So it's dynamically discovered, and like you see there is no static configuration here. So that is the whole beauty. The client will use the discovery strategy to find the server. Now, all good. Like we have server as a separate thing on our diagram. We can manage this. It's all good. Now, if you think about it, like usually in a big enterprise, this cache server will be managed by a separate team. And if it's already managed by a separate team, we can move one step further and put this part into the cloud. So cloud is still like a client server, but it's very specific. It's so specific that it can be considered as a separate caching pattern. And it's specific because the cloud part is outside of our organization. So we have this cloud thing which we ask some service provider, like in the case of Hazelcast Cloud, create a caching cluster for us and give us the way to connect into this. But it's so all these parts we mentioned before, like management, you don't need it because you just pay cloud provider to provide you a cache, to provide a cache for you. Now the thing is, like, you know, like we are in the caching domain is like, it's very strict in terms of latency. It's even more strict than databases. So you know, like when someone creates a caching cluster for you, you must be sure that the latency is low. And now how we do it, like, so the first thing, we don't own the infrastructure. Our Hazelcast Cloud is based on AWS, GCP, and Azure. You can choose. Now the thing is, you should choose the same cloud provider on which your Kubernetes cluster is run, so that they are, you know, they use the same cloud provider. So then you should select the same region, so they are in the same region and the same cloud provider. And then we even go one step further and provide you a way to do a VPC peering, so that they are really in the same virtual network, your Kubernetes cluster and your caching cluster. And then there is no even one router hop between your application and caching cluster. And that is very important. No matter if you set up your cache server or use a cloud solution, you must think about latency, because here latency is what matters. For Hazelcast Cloud, if we stick to this example of Spring, that is the configuration which you gonna use. So you click to create a cluster, and we provide you the discovery token, cluster name, and password. You put it into your configuration, and that's it. So there is no static IP configuration. And that way, with the discovery tokens, that is like most cloud solution works right now. I think MongoDB or anything like that's the way. Like for discovery, you get discovery token, and that's all. Pros and cons of client server and cache and cloud cache. From the good sides, data is separate from the applications. It's usually a must for big enterprises, from my experience. We have separate management, so we scale up, backup. It's all separate from your application. It's programming language agnostic because we use cache client, cache server with well-defined protocol. From the downsides, we need some ops effort needed or pay for the cloud solution. Latency can be higher. I mean, you must think more about it. That's the thing. And yeah, if you set up your server client by yourself, think about region, VPC, and so on. Okay, we covered like the more classic like approaches to the caching. So now something a little more modern, which fits very well into Kubernetes world. So cache as a sidecar. This is the diagram for cache as a sidecar. So the flows look as follows. Request goes to Kubernetes service, it goes to the Kubernetes pod, it goes to the application. But now the cache is not a separate thing on this diagram. It's also not embedded into application, but it's in the same pod. It's a cache server run in the same pod as application container. That's it. So the application can access the cache always on the local host because it's the same pod. But technically, it uses cache client to connect to the cache server. So it's kind of a mixture between embedded mode and client server mode. It's a mixture because it's similar to embedded because it's run on the same physical machine because it's the same Kubernetes pod. It can share the same resource pool, scale up and down together, and there is no discovery needed because we use localhost. But it's also similar to client server because after all, we use cache client to connect to the cache server. So it can be any programming language. And there is some kind of isolation between application and the cache, which may be good enough or maybe not good enough. It's on the container level. How it looks like in the code. So again, sticking to the Spring example, cache manager, we specify the static configuration for localhost, but it's not static after all, because we know that the whole system is dynamic. We just know that the cache server is run on the localhost in the same Kubernetes pod. How the Kubernetes configuration looks like, we just run 2 containers in the same pod. So we specify deployment, we specify the pod template and two separate containers. The first one is our business logic. So this is your application. This will differ from use case to use case. And the second one, Hazelcast, it's always the same as the cache server. Pros and cons of using sidecar cache. Configuration is again very simple because you've seen that was all the configuration we had to do. It's programming language agnostic, latency is low, there is some isolation of data and applications. From the downsides, again, the management is not super flexible because scaling up, down, it goes together with your application. And after all, the data is collocated in the same application pod, which again, may be a big thing, may not be a big thing, depending on your use case. It may be a big deal for you or not. The last caching pattern for today is reverse proxy caching. And this will be something totally different because in all these patterns so far, in every pattern, application was aware of the cache. So it knew that such thing as a cache exists. This time we will be different. We'll put cache in front of the application. So this is our diagram. So request before going to the Kubernetes service, it goes to the cache. And if this request is found in the cache, we don't even go to the Kubernetes service or to the application, just return the value from the cache. Only if the request is not found in the cache, we go to the Kubernetes service, to the application, and do some business logic. As of now, if you would like to use reverse proxy caching, Nginx will be your way to go. Anyway, Nginx is used everywhere, like in Kubernetes, so you can tweak it with caching. Like this simple configuration will add HTTP caching to your Nginx. And Nginx is good, because the thing about Nginx is very mature solution. So you can trust it. You can implement it right now into your production system and you are safe. However, Nginx also has some drawbacks. Like it's only for HTTP, but that's probably fine. But it's not distributed, it's not highly available. That is a problem. Data is stored to the disk. It's like actually it's stored in memory, but it can be offloaded to the disk. So it's a little different. Like with Hazelcast, you were sure that your data is in memory, so it's accessed fast. In case of Nginx, it can be offloaded to the disk, so you have to be careful. But Nginx is a very good tool, so you can start using this. But we can even go one step further and combine this idea of reverse proxy caching with a sidecar and create reverse proxy sidecar cache. And this will be the last variant for this talk. So reverse proxy sidecar caching. This works like on this diagram. So request goes to Kubernetes service. Then it goes to it's forwarded to the Kubernetes pod. But this time, it's not the application container that receives the request, but it's some, I call it reverse proxy cache container, which is an interceptor for the requests. So we inject a sidecar, which is an interceptor of all our calls. And only if it does not find cached value, then it forwards the request to the application container. And needless to say, they should form one distributed caching cluster, because we still want to have our cache distributed. And this whole idea that we put cache in front of the application, and now this whole idea that application is not aware of caching, it has some good sides and bad sides, and we need to mention both. Starting from the good side. So the good side is that you remember this diagram from the beginning of the presentation. So we have a lot of microservices. They use each other. They have versions. They are different in they are written in different programming languages, and this is a small diagram. This is generally a mess. Quickly, your system becomes a mess. Now you can look at such a diagram in your system, measure this, and you can look at this and say, I think I need to introduce caching for service 2 version 1 and service 1. And you can do it in a declarative manner. You don't even touch the code of the service. All you change is the configuration of your system and say, I would like to inject caching here and there, and that's it. And that is the whole beauty of the reverse proxy caching. So how we would inject it in like Kubernetes configuration? So this time, this could be this is actually a configuration of what we did. We did a reverse proxy sidecar prototype with Hazelcast, and that is the Kubernetes. But it's a prototype. It's not something you can use on the production right now. So this was our configuration. So at the bottom we have our application. That's clear. Then we have this caching interceptor, the caching proxy. This is the whole thing it does. It intercepts the network. If there is a cached value, return the cached value. If no, forward into to the application. But we also needed like init container, an additional init networking container. Like this container, what it did, it changed the IP tables so that any request from outside would go to the caching proxy, and any request from inside would go to the application container. Because otherwise it would be application that would receive all the requests. Now, if you think about this diagram, you may say, okay, I've already seen somewhere a diagram like this, and you could be right. It's very similar to the idea of Istio. So the whole idea of Istio is like, yeah, we have some network interceptor sidecar container, and it does some additional logic. And actually that's it. Like as of now, there is no major solution for reverse proxy sidecar caching. This was the issue like opened in Envoy proxy. And very recently, this year, this issue was actually closed. So the caching was implemented in Istio. And I think like when you finally it gets mature, a little more mature, Istio is used everywhere. So it's getting more and more popular. So I really believe that this with with the adoption of Istio and this feature implemented, reverse proxy sidecar caching, this will be the way to go. This will be the way how you do caching in a lot of use cases. So as of now, reverse proxy sidecar caching is at the phase of not mature thing, but I think it will become very popular. But I also mentioned like before that this idea of putting cache in front of our application also has some bad sides. So if the application is not aware of the caching, there is one thing that becomes way more difficult. And if you look on the internet, anywhere on the internet, what is the biggest problem with caching in general? Everyone will tell you the same. That is the cache invalidation, meaning when to decide that my cache is stale, that I should update my cache. And when your application is aware of the caching, you can use some application business logic to say, okay, I would like to invalidate this part of cache. However, when your cache is in front of your application, then you are limited to the standard HTTP things like timeouts, e-tags, basically timeouts to invalidate the cache. And this may be good enough or not good enough for you, depending on your use case. But this is like something you have to think about. Pros and cons of reverse proxy and reverse proxy sidecar caching. So the biggest pros is, and the reason why you will use it is it's configuration based. So there is no need to change applications to introduce it. It's also programming language agnostic, is everything agnostic. Application does not even know about it. And it's very consistent with the microservice world, Kubernetes, Istio. That's where the world is going. That's why I really trust in this thing. From the downsides, we mentioned invalidation. There is no mature solution yet, and it's protocol based, which may be a problem for you. So with this last pattern, we are almost done with the presentation. So as a short summary, I don't want to repeat anything I said before because it would be boring for you. So as a summary, what I propose as a summary is a very short, oversimplified decision tree, which can help you decide which caching solution is for me. So first thing you can ask is, does my application need to be aware of caching? If no, am I an early adopter? If no, use reverse proxy with Nginx. If yes, use reverse proxy sidecar with this Istio implementation, or use a prototype for Hazelcast if you are brave enough. Now, if your application needs to be aware of the caching, then do I have a lot of data or some security restrictions? If no, do I need to be language agnostic? If no, use embedded distributed cache. If yes, use sidecar. Now you have a lot of data or security restrictions. Then the last question for you is my deployment already in the cloud? Do I run on AWS, on Kubernetes on AWS, or do I deploy Kubernetes on my own servers? If you don't run in the cloud, use client server. If you run in the cloud, use cache as a service. Now, this diagram is obviously a little oversimplified, but it gives you at least idea where to look for the right caching solution. And as the last slide, I would like to recommend some resources. So the first one is blog post on how to configure Hazelcast as a sidecar. Second one is this prototype I mentioned. We did for Hazelcast reverse proxy sidecar caching. The third one is not related to this talk, but it's very good blog post about caching in general. And the last link is a very good video talk from Nginx on reverse proxy caching from Nginx. And with this slide, I would like to thank you a lot for listening. It was a pleasure to speak here.